All right, here's a for instance. Here we've got nickel tetracarbonyl, or nickel reacts with carbon monoxide to form this thing here that is called nickel tetracarbonyl. And from a structural standpoint, it basically is a nickel atom with 4 carbon monoxide molecules weakly attached to it. And at room temperature and pressure happens to be a gas, a very deadly gas. One of my graduate advisors had said that basically it kills you and it kills you again. So if you inhale this, what happens is, in the moist conditions of your lungs, this falls apart. So you've got carbon monoxide gas in your lungs, and that is going to attach to your hemoglobin and not let go, rendering those red blood cells useless for oxygen transport. So, and in large enough quantities, that's fatal. And then what happens? The nickel metal essentially plates out in the inside tissue of your lung, also fatal. So moral of the story, don't breathe in nickel tetracarbonyl. But it has a useful, it is useful for this example. So if I were to ask you what the equilibrium constant for this process is, I hope at this point you'd write down something like this. Again, products over reactants raised to the right power, so this would be nickel tetracarbonyl, divided by the concentration of nickel and the concentration of carbon monoxide to the 4th power. But let me ask you another question. Namely, does the concentration of nickel change during the course of this reaction? Not the amount, the concentration. Now remember, this is solid nickel. Think of just actually a chunk of metal. And think about a chunk of metal and think about cutting that chunk of metal in half. Does the concentration of nickel, the number of nickel atoms per cubic centimeter, does it change on either piece? And the answer is no. So while the amount might change, whether the reaction is going forwards or in the reverse direction, the concentration doesn't change. It is a constant number. And you could figure it out. If you knew the density of it, you could figure out what the molar concentration of it is. But the fact of the matter is it doesn't change. So you can say this as an intermediate step, that it's equal to the concentration of nickel tetracarbonyl divided by some constant divided by the concentration of carbon monoxide to the 4th power. And you could rearrange it like this. You could take these two constants, put them together, and say that Kc1 times that constant, the concentration of nickel metal, whatever it is, equals the concentration of nickel tetracarbonyl and divided by the concentration of carbon monoxide to the 4th power. And say that this is equal to a nu, so a constant times a constant is still a constant, which we will call this Kc2. And so the moral of this story is, well, number 1, don't breathe carbon tetracarbonyl. But number 2, to keep life simple, and because looking up these numbers just make things more complicated, we omit pure solids, and for exactly similar reasons, and so we omit terms for pure solids and pure liquids in Kc expressions. So if you were to look up in the literature somewhere the equilibrium constant for this particular reaction, the number you would find is actually this, and that's fine. You can do the same manipulations, the same calculations with it. And again, pure solids and liquids. So you are including things that are gases and solutes. And that's about it, because the other options, which are pure solids and liquids, are not in there because, again, their concentrations are just constant. So remember that. Like right now. So if you were to look back at perhaps our solubility rules from last semester, you might find that barium fluoride was probably going to come up as something that was not really soluble. And so here's the dirty little secret. Everything is soluble to some extent. It's just a question of how much, or in this case, how little. And you can treat these as equilibrium systems. So if you were to put barium fluoride solid into pure water, some amount of it would dissolve. And at some point, then it would, so the concentration of barium and fluoride ions would go up from 0 to some value. And once they reached a certain, their equilibrium, the values that give it, that reach the equilibrium constant, then those concentrations would remain steady at that point. Now remember that at any point in time, any one barium ion, for example, is going back and forth between being aqueous and being part of the solid, but overall the relative, the numbers of the barium ions and fluoride ions in solution will no longer change. Equilibrium has been reached. So the setup is, let's say that when that occurred, the fluoride concentration was 0.126 molar. And again, this is an important point. For a system to be truly in equilibrium, there must be some amount of every single component present, whether it shows up in the equilibrium constant expression or not. Now, if that equilibrium concentration for fluoride actually is 0.126 molar, what's the equilibrium concentration? And before you say it, I did not forget to give you the barium concentration. Remember, this started out with dissolving barium fluoride in pure water. So the stoichiometry might be of some help. So hit pause, think about it, scribble it down, get some numbers together, and come back and see how you did. Okay. So the equilibrium constant expression, so this is a good starting point for any problem you've got for the next month or so. It's just going to be the concentration of barium times the concentration of fluoride squared. Now remember that there's no barium fluoride term because that's a pure solid and its concentration isn't going to change. Now, and because you know that all of the fluoride and all of the barium came from this process and this process only, because I told you that you were dissolving it in pure water, that they're related, and the stoichiometry tells you that because you get 2 fluorides for every 1 barium, that the barium concentration is going to be equal to half of what the fluoride concentration is. And from there on in, it's just plugging the numbers in. So the barium concentration is 0.0063 molar. Now just plug it into the equilibrium constant expression, which ends up being 1 times 10 to the negative 6 molar. Now remember that number. And also remember these numbers right here, 0.0063, 0.0126. All right, now we know what this is, and you're going to need that for the next example. All right, and here is the next example. All right, so we're still talking about the barium fluoride solubility equilibrium. And now, a slightly different setup. Except now we are putting barium fluoride into pure, instead of pure water, it's in an NaF solution. And if you recall the solubility rules, because this is a sodium salt, this is going to be quite soluble. So you're going to have sodium ions and fluoride ions already present in this solution when you add the barium fluoride. Now, in this setup, we know that the fluoride concentration is a half molar. Now, there's no distinction between a fluoride ion that came from the barium fluoride or that came from the sodium fluoride. All that matters is that it's fluoride and that its concentration is a half molar at equilibrium. So with that in mind, let's figure out what the concentration of barium is. All right, so we know that the equilibrium Kc expression is just going to be barium concentration times the fluoride concentration squared. Now, we already know Kc. We were told the fluoride concentration. So then it's just a matter of rearranging and solving for the barium. Now remember, we can't use reaction stoichiometry here. You're not just going to say, oh, isn't it just 0.25 molar? Because this number contains fluorides from the barium and the sodium. You don't know which is which. So you have to get it by manipulating the equilibrium constant expression. And that is done here. So you've got barium concentration is going to be equal to the Kc divided by the fluoride concentration squared. And we know what that is. So we just use the Kc from the last example, 1 times 10 to the 6th divided by 0.5 squared. And that gives us an equilibrium concentration of 4 times 10 to the minus 6 molar. Now let's think about this for a second. The barium concentration from the last slide in pure water, the barium concentration at equilibrium we figured out was 0.0063 molar. Now, in this system here, the barium has to come from the barium fluoride. It's the only source of it. But notice how much smaller it is. So instead of being, let's put it in scientific notation reference here. So this is 6.3 times 10 to the negative 3 molar. So this is about 1,000 times less. So what this means is that the presence of fluoride from the sodium fluoride reduced greatly, by about a factor of 1,000, the amount of barium fluoride that could dissolve relative to pure water. And this is called the common ion effect. Fluoride is common to both the barium fluoride and the sodium fluoride, and will be the subject of a section in a later chapter, so just be aware of that. But so the fluoride, the sodium fluoride, made a difference, and it reduced the solubility of the barium fluoride.